Good morning. I'm Johnny Duke, and we're going to be looking at exponential applications. My students always ask me, when are we ever going to use this stuff that we've been looking at? Well, your eyes should light up because we're going to be looking at least at one of my favorite topics, which is what I would think is one of yours as well, money. In this case, exponential applications can go around compound interest. Now, before we go to compound interest, let's look at a scenario in which Bob is putting money in the bank, but Bob's not very bright as an investor, and he allows the bank to talk him into simple interest. So Bob puts $500 in the bank at 6% simple interest per year. So let's look at how much interest does the bank owe Bob at the end of 1 year, if that's the time period. Well, if you'll recall from previous classes, simple interest equals PRT, where we're looking at principal, which is the amount of money that Bob puts in the bank, times the interest rate, which is 6%, times the time, in this case, 1 year. And so as we look at that, Bob will draw the interest will be $500 P times the rate, 0.06, times 1. Notice with the rate in our formulas, if it's 6%, we need to write that as a decimal form, 0.06. And he will get $30 interest at the end of the interest period, which is 1 year. What if Bob does that for a 10-year contract with the bank? How much interest does the bank owe him at the end of 10 years? Well, very similar process that we'd be looking at. His interest would be his principal, the amount of money he put in the bank, $500, times the rate, 0.06. This time T is 10. And that would be a grand total of $300, which doesn't sound all that bad, but we'll find out he could have done much better than he did do. So let's look at this from a little bit different perspective. Instead of finding the interest, let's find out the amount of money that Bob has at any given time T. So we're going to look in this scenario, how much money does Bob have in the bank at the end of 10 years? Well, the amount will be $500, that's what he put in the bank, plus $300. That's going to be the amount of interest. Or if we wrote that symbolically, we're going to be looking at the amount equals P plus interest. And that equation is then given as A equals PI, P plus I. But since I is PRT, principal times rate times time, we can substitute for this I PRT, and we get a new but similar formula, A equals the principal plus PRT. And we can work a little bit, we can actually put our numbers in for Bob. It would equal 500 plus 500 times 0.06, and I'm going to leave T as the independent variable, meaning as it changes, so will the amount of money. And in this case, if we simplify, since 500 times 0.06 is 30, we will get A equals 500 plus 30T. So if Bob uses simple interest to gain on his investment, he will be looking at the amount will be his $500 plus 30 times however many years that he leaves the money in the bank. Now, let's look at that for a minute. As you look at this equation, that for simple interest, what type of equation is this? And hopefully you recognize it as a linear equation. And the slope of our line is 30. The y-intercept of the line is 500. So at what rate is his money growing each year as long as he's having simple interest? And the answer is $30 per year for every year that he leaves the money in the bank. And let's look at a second scenario, one that now brings in our exponential applications. Bob wises up as an investor and he says, I'm going to demand that the bank pay me my interest each year and then add that interest to my principal so that that will be calculated in the next year's interest. Let's look at what that does to Bob. We're going to use our simple interest formula to find out how much money Bob will have in the bank at the end of 1 and 2 and 3 years. We've already seen 1 year. He puts in $500. He adds to that his $30 interest, and at the end of the first year, he has $530 in the bank. But now remember, the principal is no longer going to be $500 because he's demanded that he be paid interest on the entire amount of money they owe him, which is $530. So at the beginning of the second year, he has $530 in principal. Now, we calculate his interest based on $530, and it'll be $31.80. Hence, he'll have $561.80 in the bank at the end of 2 years. But he says, wait a minute, now my new principal is going to be the $561.80. We will calculate the interest based on $561.80. In other words, that number times 0.06 times 1. And at the end of 3 years, he'll have $595.51 in the bank. Now, we could continue this from the 3rd year all the way to the 10th year in a very tedious set of calculations. But in mathematics, we're always looking for what's a shortcut. Well, in this case, a shortcut is a new formula. And let's look at what that new formula actually is. Now, as we begin to look at it, notice this formula is for finite compounding. Finite in mathematics means that we can count the number of times that it's going to be compounded. So we've got a new formula, and here it is. The amount will equal the principal times 1 plus r over n to the nt. Now remember, for a particular case, we're going to know what number p is. It's going to be a set interest rate. We're going to learn about this n. But the real important variable's out here, t. Notice now where t is. T is in our exponent. Hence, these are called exponential equations. So, let's look at this formula a little more carefully and look at each part of it. P represents the principal. Remember, in Bob's case, that was $500 that he started with in the bank. R represents his interest rate. That was 6% in Bob's case. Now, the new part of this is N. N, you will see, is the number of times that the interest is compounded in the interest period, meaning that if Bob is earning 6% per year, then N is the number of times per year that the interest is going to be compounded. So let's take a look at what Bob will get over time. If Bob has $500 in the bank at 6% interest per year, and T is the time, if he is looking at annual compounding, annual means once a year. So N is going to be equal to 1. We plug those in our formula and we get 500 times 1, that's part of our formula, remember, it never changes, equals the interest rate, 0.06, over N, because this is annual compounding, N equals 1, to the NT. Okay, and let's look at some particular years that Bob will make, how much money Bob will have in his account at some particular years. In this case, I'm letting T equal 1. And if we put that in our finite compounding, since this is compounded only once in that 1 year, essentially Bob has $530 in the bank. Now, if you look at the bottom of the screen, that's the keystrokes you would be doing on your TI-84 calculator. You'll hit 500 times, and then be sure and use parentheses. Left-hand parentheses, 1 plus 0.06 divided by 1, close your parentheses. Now, on your TI-84 calculator, on the right-hand column, under the clear button, you see what some people call a caret or a hat button. I tend to call it a hat button because it looks kind of like a hat over a number. You hit it. That's the exponent button, as we've seen before. And I put these in red on our PowerPoint because those parentheses are extremely important. If you leave those out, you will actually wind up miscalculating the amount of interest. And so as you put that in, you get 530. Well, let's look at some other scenarios. What if Bob is using annual compounding for 5 years? Well, everything stays the same except T is now 5. And notice at the end of 5 years, when you do the calculation, Bob will have $669.11 in the bank. What if we change that to the 10 years? And we'll compare that with the simple interest here in just a moment. Well, if he's compounded annually, which again means N is 1, he will take 500 times 1 plus 0.06 over 1 to the 1 times 10. And when you put that in your calculator, you get $895.42. Now remember, when he did simple interest, in which case his interest was only calculated one time at the end of 10 years, he had only $800 in the bank. By demanding that he be paid interest at the end of every year and that be put into his principal for the next year, compound interest then, Bob has picked up in that 10 years another $95.42. He's increased his investment quite a bit. Now, let's look at what happens if we change that to 20 years. Okay, still annual compounding, N is 1, and in this case, we're changing our time to 20 years. Let's go to the Smart View calculator just to see how that would work with several of these numbers. Okay, so I'm going to put this in. We're looking at $500. So we're going to take 500 and we're going to multiply that 500 parentheses 1 plus 0.06, his interest rate, divided by the number of times it's compounded is 1. And then we're going to close the parentheses and raise it to the, in parentheses, remember, 1 times 20. And that is how we got the $1,603.57 that we noted on the PowerPoint a minute ago. Now, if I want to simply change that time to 30 years, let's say, I could take and hit second and enter, and now I can arrow back, and the only thing I'm changing is T from 20 to 30, and so I'll change that 2 to a 3, which gives me 30 for our time, and notice I get my new answer. He would have $2,871.75. So let's go back to the PowerPoint now that you've seen how to do that on your TI-83 calculator. Let's say in this case, Bob wants to change to quarterly compounding. You know, he liked getting interest once a year. Now he says, wait a minute, he's getting a little greedy, to be frank. But let's say I want interest to be paid every 3 months or quarterly, which would be then 4 times a year. Notice in our formula, now we have N is 4, and that changes two different places in the formula because n is there twice. And he will have $1,645.33 if he maintains his money for 20 years at quarterly compounding. Let's go two more scenarios with this. What if he goes to monthly compounding? Well, now n in our denominator and up here in our exponent, instead of being 4 for quarterly, is 12 for monthly compounding. And notice he picks up a few more dollars, $1,655.10 after 20 years. Now remember that his initial investment was $500. So if I subtract that $500 here, he's made $1,155.10 in interest alone over that 20-year period. And the final example we'll look at with finite compounding. Remember, finite means a set number of times or a countable number of times, is daily compounding. Now in my scenario here, I use for daily 365. Banks very often will use 360 if it's financial. In science problems, we would tend to use 365.24 with leap years. But I'm just using 365 as an arbitrary choice for 365 days in a year. So daily compounding, n becomes 365. Notice that affects the denominator and one of the numbers in our exponent. And he'll pick up a few more dollars still. After 20 years, his $500 will have turned into $1,659.89. Now, Bob says, whoa, every time I've changed that n, I get more and more money, even though it is slowing down, as we'll see. So Bob gets really greedy and he says, look, I want to be paid continuous interest. In other words, every time, and in fact, faster than I can click my finger, I want to be paid interest. And that becomes then continuous compounding, or we would call it infinite compounding. So in this case, we're going to need a new formula. And that formula is going to take the old one, do a little bit of calculus to it. So we're going to avoid that and just introduce our formula down here. Bob is going to be using for continuous compounding or infinite compounding. We no longer have an n because n is going to infinity. We have the amount equals p times e to the RT. Some people remember this as the PERT formula. So in Bob's case, his principal remembers $500. E is that natural exponential number that we looked at in one of our previous sections that I told you we would have plenty of applications with, to the 0.06 times 20. And so if he gets continuous compounding for 20 years, he adds just a little more money to what would have happened if it had been daily compounding. Now he gets $1,660.06. Now let's summarize what we've learned so far in this case. And this is the case where we would have 30 years. We simply change the 20 in our exponent to 30, and he has $3,024.82. So in summary, we can look at a couple of effects of compound interest. In the table below, note the results of the compound or the amount after 10 years for a $500 investment at 6%. So in other words, it's always $500, 6% for 10 years. What's changing is the type of compounding. If we have no compounding, we're back to simple interest. And remember, Bob's $500 at the end of 10 years with simple interest had become $800. When he asked for annual compounding, remember that means that n is 1. It's compounded once a year. Bob's amount increased to $895.42. And so Bob said, whoa, wait a minute. I want to have this compounded 4 times a year. And when he did that, his investment grew to $907.01. He picked up roughly, about $8 with that compounding. And so he says, well, let's go 12 times. And he picks up another couple of dollars. Let's go daily, 365 times a year. He picks up another just over $1.30. And finally, when we thought that he would really pick up all kinds of money by going to continuous compounding, he really only picked up 5 cents over a 10-year period. And so we see out of this that the more times you compound, the better off you are, but it really begins to slow down the more times you compound, which is kind of ironic. Now, there's also a second effect, and I think this is the most important effect. If you don't learn anything from the work that we do with exponential functions and with logarithmic functions, other than the power of compounding, especially with money, which would help you in retirement, you need to learn this lesson, and that is the power of compounding. It's shown in this table. We're going to take Bob's investment of $500. We're going to give him 7% interest because he's been a good investor. He's going to have this for monthly. N is going to be 12 in each one of these investments. And we're going to look at what's the amount of money that he has at different times. Well, when time is 0, in other words, when Bob first puts the money in the bank, he has $500 in the bank and he has 0 interest earned, which makes sense. After 10 years, if Bob invests $500 at 7% interest with compounded monthly, at the end of 10 years, using our formula, you would find that he has $1,004.83 in the bank, which means that in that 10-year period, he picked up $504.83. He doubled his money. Now, if you go from 10 to 20 years now, you put that in your formula, the finite interest formula, you'll find that after 20 years, his $500 will have grown to $2,019.37. This is where it gets really interesting. Remember, in that first decade, he picked up $504.83 in interest. In the second decade, he picked up the difference between these two numbers is $1,014.56, and that's all interest. If you go this for 30-year period, Bob's going to have $4,058.25 in the bank, and in that third decade, he's going to pick up $2,038.88 in interest only. And finally, if he would keep that $500 in the bank for 40 years, he would have $8,155.71 in the bank at the end of his 40-year period. And in that last decade, he would have picked up another $4,000. So if you were looking at this at 7%, it will change with your interest rate. It could be more, it could be less. But at 7% interest that is compounded on a monthly basis, about every 10 years you double your money. Not bad for an investment. So, you say, there got to be other applications as well. And there are other applications. One that we'll look at briefly is population growth. One way to model population growth is to use a very similar formula. A, the amount of people in a population at any given time, equals a sub 0, we're going to talk about that sub 0 here in just a minute, e to the kt. Now notice that's essentially the same as our continuous compounding formula for money. And so what does the k represent? Well, if you look at k, it's in the same place that r was in the continuous compounding formula. So k is representing r, which was the interest rate. In this case, it'll be the growth rate. And what about that a sub 0? Well, a sub 0 stands in the same place that p does in the continuous compounding formula. And p was the principal, which means that's the amount of money that Bob had to begin with. And so a sub 0 will be the population when we begin counting the population. In other words, at time 0, hence the subnotation 0. So let's look at a scenario with this. Suppose that the population of Rome, Georgia, is estimated by A equals 90,500 e to the 0.021 t for years after 1990. So in other words, remember, time is going to equal 0 in 1990. What's the population in 1990? Well, in 1990, we just noted t is 0. So in our formula, t will be 0. If you put this in your calculator, well, actually, no need to put it in your calculator. You'll get e to the 0.021 times 0 is e to the 0, which is 1. 1 times 90,500 is 90,500. That is a sub 0 in our formula. What's the annual growth rate in this case? Well, the annual growth rate is k in our formula. And k is 0.021, or written as a percent, 2.1%. Meaning that it's estimated that about that time period, Rome was growing by 2.1% per year. Now, what's going to be the estimated population then in 2010? Well, in 2010, we're going to have t equals 20. 2010 minus 1990, which is when we began counting time. The amount then will equal a sub 0, 90,500, e to the k, 0.021, t is 20. And when you put that in your calculator, you'll see that the estimated population for Rome in that time would be 137,738 people. Now, we've looked at a quick example with population growth. In future lessons, we're going to be looking not only at population growth, and we'll be able to do some things that we can't do right now with the math that we've learned so far, but we'll also be looking at exponential decay. In other words, things like in science, radioactive decay. So, we'll be looking next time at the counterpart of exponential functions, which are logarithmic functions. Thank you.